And now I will introduce simple harmonic motion and similarities with circular motion. And this is really actually from math, where we're gonna have the x and y, and this is really the circle that the object is moving on. And if I will have initially my object was somewhere, let's say here, all right, then at t equals 0, my object was here, and then it did move to here, and this angle, this amplitude or this length is a. This one, we can say we're gonna call it phi. Then this piece here, it is x at any moment. It's gonna be x equals a cosine phi. Then this is the equation that is gonna describe how x is depending on the angle. Now that phi, the angle, it is equals omega times t, and omega, it is the quantity that we defined later, angular frequency. This equation can be written in so many different forms. It can be written as x equals cosine 2 pi ft. It can be written as a cosine omega t. It can be written as a cosine 2 pi over t times t. All of these are really, I will say, valuable forms of the equation. Now remember here, f, it is the frequency, and it is the number of cycles per unit time. It is measured in hertz. And t, it is the period of the motion, which is the time needed to complete a cycle, and that is measured in seconds. Anytime we are going to choose this to describe the displacement as, okay, I'm gonna have just one form of it. X, this is, I am describing displacement per unit time. Now this here, let me have another color. This one should be in radians. Then you're gonna change the calculator into radians. Now Vx, of course here, we don't have calculus for this class, but we know that V as a function of time will be the derivative of that. You don't have to know how this was derived, but you're gonna know the form. Also, we know that ax, which is the acceleration, is the derivative of velocity with time. Then it is minus omega squared a cosine omega t. Then these are really the three equations that we are using. Remember here, x is not constant, velocity is not constant, acceleration is not constant, and I will say always we are going to use the same this dependence on time as sinusoidal. Now let's do one example here. Then I will say a simple harmonic motion was described as x, it is 12 cosine 0.25 times t. Now the question is also saying that x is measured here in centimeter and t in seconds. Now the question is asking for find the period of the motion this is A. B, the velocity at t equals 2 seconds, and C, it is the acceleration at t equals 2 seconds. Actually, this equation we can derive from it so many quantities. If we compare this one with the general one, okay, then we know here that the first omega is 0.25 radians per second. We know that omega, it is 2 pi times the frequency. I can calculate the frequency, but they are not asking about it. They are asking about the period. Okay, then this is the relationship between omega and t. Then t here, it is 2 pi over omega, and that is 2 pi divided by 0.25 radians per second, and this is 1/4, then it's going to be 8 pi. All right, this is 8 pi seconds, which is about 25 seconds the period is. Vx, it is negative omega A cosine omega, sine sine omega t, and that is negative, and here this is, we know that it is 2.25 radians per second. The amplitude, it is 12 centimeters. Sine, now here 0.25 radians per second times 2 seconds. This will be negative 1.4 centimeter per second. In the same way, I can remember here, when you're gonna enter this number into your calculator, this one, your calculator should be on radians. AX is going to be negative omega squared A cosine omega t, and that will be negative 0.25 radians per second squared, 12 centimeters, and then here cosine 0.25 radians per second times 2 seconds. Again, this one here should be in radians, and that is negative 0.66 centimeter per second squared. I'll stop here and then I'm gonna share another video with you. Thank you.